Actually, there's a lot of resonance with this. I think as you heard from the two previous discussions, clearly leadership class computing, whether it's exascale or not, is more than just the system, the software, and the human expertise. And I'll talk a little bit about human expertise, not necessarily in the normal sense, but in the sense of community building and development. At NSF, we view, as the others do, our investments represent a national asset. And so when we make investments, we do it in that bigger context of what's happening internationally, both from a science and engineering point of view, and what investments are other entities making. I just outlined, we've had excellent success with our own system, Blue Waters. Oops, no. But not success with the slides. I didn't touch anything, so I'm not sure what happened. It's disappeared. Nothing works. The computer shows it.
Looks great on the computer, but it looks nothing up there. Go back down here. Back to the slideshow, see if it works.
Sorry.
Oh, okay. Oh, that's not your fault.
Thank you.
Something's acting funny.
So I also wanted to indicate, because this is a theme you'll see elsewhere, that there are investments made not just in instruments or the hardware, but also in software and applications by other agencies, NIH, NASA, DOE, DOD, and those are also important assets as we think about leadership computing and what our own investments should be. As I said before, looking at contributions to economic competitiveness as well as training the next generation is really an inherent piece of the leadership computing investments that we make. And so a little bit building on the Blue Waters experience at the University of Illinois at Urbana-Champaign. It's nearing the end. It's been 5 years. These represent the kinds of results that one might have anticipated in the beginning. So plasma simulations, hippocampus simulations, modeling of supermassive black hole mergers, space weather models, et cetera. And so we do see a breadth of research that is being served by this system currently, but we've also had areas where we had unanticipated results, just like you would expect with a really novel instrument and expertise. And in particular, these investments serve as really ways to stimulate bringing together new kinds of expertise on either methods or problems that haven't been approachable before. In this particular case, this was just actually released yesterday, although it started last year. And it was really mapping, high-resolution mapping, first of the Arctic. And it was first time anything of this magnitude had been done. And again, not the normal application we would have thought about when Blue Waters was funded initially. But it involved a collaboration from University of Minnesota, from the National Geospatial Agency, also not on here. Esri made all of the information available publicly through AWS. So again, I think these activities, these investments really stimulate innovation, collaborations, and it's really important, as Doug said, to position yourself so that to anticipate this. And so, you know, in the bigger context, one might have traditionally have seen leadership computing as, well, you had the Branscombe pyramid originally, but that model isn't right for today, and you could see evidence of that in the other presentation. And so while we have these categories of leadership, innovative, campus, distributed, federated, the notion that these are distinct and there can't be combinations of two of these is really gone. We're in a space now of a lot of disruption in technology, a lot of change in how science is being conducted. And so really examining the whole landscape, not just what we fund, not just leadership class, is really the vantage point that we're taking when we think about what leadership computing is for the future. So, and the notion of cloud services and how that plays in this environment of how prototypes, how you allow innovation into this environment without having to recreate all your applications, and how you coordinate and measure across this landscape are new challenges that I'm not going to talk about, but there are activities going on in that space. So I am going to spend a little bit of time, again, you saw reference particularly in the EU presentation about looking at the whole landscape, even beyond the computing that I described. And so I'm going to give you a few examples, just a few examples of how this is playing out as we look to the future. So about in mid-2015, NSF announced the instantiation of the big ideas. And there were 6 research topics that were identified: quantum leap, understanding the rules of type, predicting from genotype to phenotype, navigating the new Arctic, and then multi-messenger astrophysics that I'll talk a little bit about, and then work at the human technology frontiers and harnessing data. And I'll also mention these two in particular. This one plays out significantly as we think about leadership computing, because many of the scientific frontiers that we see today are increasingly convergent from a disciplinary perspective. So that, again, plays into the complexity of what we want to achieve. And the other underlying theme, of course, being a cyber infrastructure person, when I see big research, I see a big cyber infrastructure, but it is true that there are challenges and opportunities. So I'm going to start with the example of LIGO because it's probably well known. So LIGO was, from an instrument perspective, was the single largest investment that NSF ever made. It was hundreds of millions of dollars over 10 plus years. And it's two interferometers to detect gravitational waves. A big idea, long-term, 10, 20 years in the coming. First time didn't actually work. But to actually be able to detect, which was in 2017, the detection, the Nobel Prize in 2018, took an enormous amount of computing, collaboration, software, and not just on the application side to do the detection. There were massive simulations. When this was started, Einstein's 10 equations had not been solved, so no one knew what 2 black holes colliding looked like, even if they detected it. So that was really a leadership scale simulation. And then the massive parallel event searches happened on systems internationally, by every agency, by labs, by academics. I think the paper that was finally published on this was actually 1,000 people were on the paper. from all over the world. And so it required a lot on the computing side, and not just on the application side, but the workflow has become increasingly complex. It started with essentially volunteer computers held together by the Open Science Grid, with Condor as doing research management, Globus moving data around. So I think it's useful because while there are many individual researchers working on this problem, much of the computing, much of the software, much of the infrastructure, the interferometers were shared resources. And so we see that particularly with respect to the instruments and observatories, this really being a driver, the streaming data, the complex workflows. I'm not going to talk about, but clearly as we move into the machine learning space, the emphasis on the transparency and credibility and correctness and security not just being protecting from intrusion, but protection from unintended intrusions. And again, others have talked about this. Kathy Yellick gives a wonderful talk on this. And the other part is the technology side. It may seem trite, but the signals are all there that this pace of disruptive technologies is only increasing, not decreasing. So the role of the software, and not just the application, but the middleware, in taming that complexity is increasingly significant. And I think even from a leadership point of view, the role of clouds, in particular multi-clouds and hybrid environments, has to be a consideration. So, this while I'm not going to talk about solutions in this is the landscape in which we're really trying to create the next generation of computational and data science at scale. So I want to use a very recent example as just indicative of what is happening and how it has to come about. So I mentioned I didn't mention, the Large Hadron Collider in CERN actually has the detection of the Higgs took 250 petabytes of data. It took 100,000 CPUs for 2 years sustained to actually detect the Higgs. And there are instruments being funded both by DOE and NSF targeted to the next generation of experiments to look for physics beyond the standard model, beyond the standard theory of physics. And so these are very important fundamental questions. And these instruments will be available in the 2025-26 timeframe. And in order to deal with that additional magnitude of data and science and order on each side, you have really some convergence of computer and data science, applied math, and software engineering, because of some of the simple approaches that have been used heretofore will not work anymore. The software has to be much more shared in a community software, and it's a very large international community. So there was an award just made, I think within the last week, that resulted from initially workshops, then 2 100-page reports that outlined what was really going to need to happen from a software point of view in order to be able to do the types of experiments needed. And so you can see it's quite a complex undertaking. 21 researchers, 17 institutions, it's international. And it's located, the PI is in Princeton, but it's quite a large undertaking. And we do expect it to transform the operational services. This is for the researchers. And the reports did not really delve into the computing model, but we know it'll be essentially a leadership class computing, but we don't really know yet what the possible computing models could be to satisfy that. But anyway, so that's one activity that is going along in conjunction with the upgrades to the facilities. And this is in an earlier stage. So this does, MMA is multi-messenger astrophysics, and it really builds on the success of the gravitational waves and adds in the ability to combine detection of gravitational waves with particles and electromagnetic radiation. Again, this is unsolved, hasn't been done. The initial efforts have started. There's a international workshop going on that has happened. An initial report has been published, and next steps in the planning. It's clearly going to involve some interdisciplinary convergence in astrophysics, computer science, mathematics, and software engineering. We don't have any of it in place. It will absolutely require multi-agency coordination among NASA, DOE, as well as international parties. And I wanted to just go through how this is evolving with these events. This is the two black holes colliding. That effort was done by, the detection was done by the interferometers in the US. So that was done in 2000, well, it's labeled as 15, but published in 17. And it still involved, as I said, about 1,000 researchers all over the world. The second one on the top, which is much more recent, was the neutron star merger. And in that case, it involved both the interferometer in the US as well as Virgo, an interferometer in Europe. Again, many researchers, and as I said, understanding what the simulations were and how these mapped onto it. This last one was IceCube, which is at the Antarctic. It's an instrument in the Antarctic in the deep below the ice. And it shockingly detected extragalactical neutrinos. And that happened within the last couple of months. But what's interesting about that is it wasn't just the IceCube that was involved in that. It was also NASA's Fermi, the Gamma Imaging Telescope, and it also involved 20 ground-based and space-based telescopes. And the point here is that what is starting to happen with these activities is you get a signal and immediately you point other instruments of different types, be it gravitational wave or particle or the electromagnetic radiation. You have to analyze it quickly and immediately point those devices to see if you can get additional detail. And that's the way discoveries are happening. And so it's not just an instrument and a computer, it's multiple instruments, international collaborations, and a quite demanding computational load. And how one does that discussion of evolving what that needs to be for the future has to engage the research community in thinking about their problem as well as the computer scientists. So, so this one is not quite as far along, but will, I am sure, have enormous demands. In the meantime, our current planning for OAC is the group within NSF that funds most of the large systems except for the one at NCAR. In the meantime, we have been concentrating on a successor leadership class system, a phase 1 system, as well as planning for the rest of the portfolio to support the research community. And nearly at the end here, but we did issue a solicitation last year looking for at least 2 to 3-fold performance over blue waters, looking at the known plus the future, and then also supporting alignment with the facilities. And with the idea that it would, of course, include education and industry outreach, but would also lead to a phase 2 that would be 10 times greater than the 2 to 3 times. So in August, the National Science Board approved the acquisition by the University of Texas at Austin at a system for $60 million, as well as $8 million to begin the phase 2 preparation. And this is thanks to Dan Stanzione. Just a little bit about that system. It was announced officially last week. It'll be deployed almost immediately in 2019. And it'll be for 5 years with planning for a phase 2 systems with 10 times the capability. It's the University of Texas at Austin through TAC, Ohio State, Cornell, Texas A&M. And the phase 2 planning is described in there with a number, again, of collaborators. It involves a number of vendors as well, quite a large number of vendors. The primary system is Dell EMC and Intel at 35 to 40 petaflops, interconnect more or less standard DDN, 50 petabytes of disk. It also has the single precision, again, anticipating some of the machine learning opportunities, and a front end for data movers and workflow, again, getting ready for those workflows. It will interface to other infrastructure. It also has, in its operational role, will connect with cloud providers, particularly Microsoft, Amazon, and Google for the data side, and partnerships in education and workforce. It's about 6 megawatts of power, direct water cooling, oil, experimental oil immersion cooling, solar and wind as a. So I think the conclusions are pretty benign, but I think the emphasis on the agility of the ecosystem and how the leadership fits in is really a crucial element, and you could see that from the other presentations. The application requirements are changing dramatically, and we have to involve the environment. And so with that, I think I'd like to thank these people who really provided me the information that I presented today. So, thank you.
Thanks, Irene. We heard from the European Commission or Union. We heard from DOE, pretty extensive plans for how to make the ecosystem work, how to fund it over a period of time. I know that the NSF has CI 2030 going on, and there's really no sort of forward view aside from the leadership class investment as to how the pieces will fit together in the NSF's mind. You also make reference to a lot of other players like campus facilities.
Right.
So how is that going to evolve? Is the NSF going to put out a plan of its own about how it's going to operate in that space, or is it looking to the community to build that plan?
So the answer is some of both. So I think most of the resources that researchers use today, the academic community use, most of those are provided by the university. And I don't see that changing. However, there are things that we can do to both make those investments more useful, to acknowledge that research collaborations across institutions are happening more and more frequently. And you saw an early example of that with the Open Science Grid, which was essentially volunteer and trying to make that more of a community asset. And I think I think we have to take that to the next level. And what does that mean? We did some experiments starting about 3 years ago with Cornell, University of Buffalo, and I think it was USC, where they were trying to actually do load balancing across and bouncing to a cloud provider. And you definitely see trends of hybrid models. And so I do think that has a role in the picture. So, and we're going through that analysis now. And some of what the computing model, some of these activities needs, these aren't the only research efforts going into plan. What is the software needed? What is the computing model? So those are playing into it. So we'll have to see what happens there. The other area that I think needs our attention is what I would call in the middle layer. It's much too confusing a space now. And I think with the software and the software frameworks, and I think the engagements we're doing with the various communities, I think we have a path at the application level, but that other level is really, at least I don't know how, and I think that needs more attention from us. I hope that answers the question.
Hey, Irene, how are you? On the cloud stuff, so you have that as kind of a burst resource or a data access resource, but do you anticipate deeper collaboration with the tier 1 cloud providers on methodologies around AI or algorithm development and kind of integration in these workflows?
We have some activities going on now, mostly in the computer science area. And yes, I do envision more, we are having those discussions. I think the area that right now is not very well explored is multi-cloud and data egress and all of that. And so that's going to take some experimentation, more experimentation. But the data hubs, the big data hubs, 3 of the cloud providers have provided cycles, and there have also been on the LIGO, AWS provided cycles and egress, waived egress. Right, so we're doing still experiments, but more has to come there. Yeah, so I do envision more.
Yeah, it just feels like, and I've been part of this community forever, so it still feels like it's kind of like this community feels like it's isolated from the broader dynamics and what's happening in markets and ecosystems, and
Yes.
They have to be part of this conversation, not just as, sort of supporting from cycle and infrastructure, but they are challenged with the same scaling and latency and
Yes.
workflow dimensions. They have to be part of this conversation.
And you do see, you do see industry also coming to grips with that, of not wanting to
Absolutely.
be locked in and,
Absolutely.
held hostage and things like that. So I think there is alignment and possibility there. And it's clear that the service model that goes along with the cloud is something we need. Absolutely. Yeah. Sorry.
Yes, thank you. From the European point of view, a question. So what about the long-term data preservation and curation? Do you plan some kind of horizontal cyber infrastructure, or is it going to be mostly vertical cyber infrastructure? And how do you see that?
So I would, could everyone hear the question okay? It has the long-term data. So it's a little bit, it's always complicated. But, so there's two things. First of all, there's a lot of data sharing going on now, and there are some long-term. Astronomy, for example, has a history of both deciding what to save long-term and deciding what not to save long-term, those are companion decisions. You can't have one without the other. But it is true still that communities are in very different places. And it's also true that their needs are not the same. So, and then the third thing that is a little bit different in the US and relates to NSF and doesn't relate to Europe is that, the intellectual property which is represented is not ours. So when we fund a research award, we do not capture the intellectual property. I mean, we're taxpayers so we don't own that. So on the facilities, we certainly can do that, the long-term facilities, but for standard research, we don't own it.
Irene, I have a question.
Yes.
So over the years, there's been considerable investment in NCSA, both in terms of physical infrastructure and, more importantly, human infrastructure. Blue Waters is at the end of life. Are there any future plans there?
So I don't think I can comment on that, to tell you the truth. So, but I want to say that this is an issue that comes up frequently, and the larger issue of sustainability versus competition, and getting that balance right. And it doesn't just happen on the computing side, it happens on the facility side, it happens. So what's the right duration? There was a National Academy study in 2016 related to computing that recommended to us that we look to a longer-term commitment for our very largest investments, and that's why you see the phase 2 as a facility investment, which gives it a longer time horizon than Blue Waters had. So I can say that at least.
Any other questions? Irene, thank you.
Thank you.